Good evening, TSC panel members. I am Madhumita Mallick. I am a PhD student in the Department of Computer Science and Engineering. And today I will be presenting my synopsis seminar. I am advised by Professor Niloy Ganguly. The topic of my seminar is Techniques to Facilitate Seamless Identification of Activities of Daily Living in a Smart Home. So let's go ahead and start. The outline is basically that I'll start with giving you an overview of the thesis, and then we'll talk about the objectives, give you a little background, and then jump to the chapters and the different problems that I have handled, and end with summarization of my thesis. So, okay, let's start with the overview. So, as you can understand from the title, my topic is really smart homes and human activities of daily living. And by smart home, I mean that a home that is equipped with sensors that can sense and give you some information regarding what the person is doing. And by what the person is doing, I mean that what activities they are performing. So basically what we will do, as you can see in this picture, is that a smart home is associated with many sensors, and they can be attached to different devices or in the wall. And then when a person is doing an activity, in this case cooking in the example, they are interacting with various sensors. All the data is getting stored, and through a gateway it is going to the cloud or a server where a machine learning algorithm is analyzing this data, in this case activity prediction. And after you have predicted what activity is happening through a machine learning model, the caregiver or a recommender system will basically control or assist with the application, in this case remote healthcare. So that's how it works, the smart homes and the activity detection system in smart homes. And by let's talk about human activities of daily living, what we mean by them. So in this thesis, we'll talk about the course activities like cooking, eating, showering, which are really consisted of many small events. And research has found that proper completion of activities of daily living indicate towards a person's well-being. So the question that we ask is, detecting ADLs by monitoring smart home sensors are straightforward, whether they are straightforward. Turns out they're not. So there are many challenges. The first and the foremost is that activities uses heterogeneous sensors. There is no one dedicated a sensor for an activity. So if you see for cooking, there are many sensors are getting activated, and in the graph you can see that for each ADL there are many sensors that are associated. At the same time, one sensor can be associated with many activities. So one activity uses multiple sensors, and one sensor uses multiple activities are getting activated during multiple activities. If you see here, the fridge is also used for cooking, drinking water, and storing food. If you see the graph, the activity usage per sensor is really high. So that is challenging, since there is no dedicated sensor for one activity. The next challenge is that we are human who do not do one activity at a time. We hardly do one activity. We interleave activities with one another. If you see the top graph in the right hand side, eating is associated with wash dish, meal preparation, housekeeping is associated with leaving home or entering home, and such and such. So when you basically interleave these activities, the events that come together gets really multiplexed and the frequency is high. So that is one problem. The second problem is that there can be many errors in this sensor stream. There could be some permanent sensor faults or some missing alarm events, which will hamper the sensor stream, and at the end hamper the ADL detection algorithms. The last challenge, and very important challenge, is that there is a huge number of data that is getting generated. So the ADL detection algorithm will have to be complex enough to handle this amount of data which is getting generated for both its training and testing. So keeping in mind the challenges of ADL detection, let's talk about the objective of this thesis. So the first objective is that how do we demultiplex sensor stream? So if it is coming from different activities and getting multiplexed together, or different, so how do we really see a sensor stream and then segment it properly by identifying right combination of discriminative features of human activities. So that is the first objective. The second objective is to find and isolate both missing and false alarm faults in a census string. So we'll try to find an error that may have occurred in a census string in a unified manner. The third is to build an end-to-end data management solution that is comprising of two things. One, we try to grade the data, understand the context, and then try to do some sort of storage optimization to improve the throughput of the end application. So these are the three objectives. And keeping that in mind, we will talk about the contributions. So the first objective, segmenting the census stream, is the first chapter, TSFS. The second objective, to find and isolate errors in a census stream, is the second chapter, DETECTIF. And the third problem of data management in smart home is divided into two chapters. The first chapter, SmartGrade, talks about those smart home sensors data, where smart home sensors are like motion sensors, context sensors that are deployed and give binary, event-based or value-based value. And the fourth chapter is the same problem. We handle data management, but for multimodal sensors. So if there are video sensors, if there are wearable sensors, how do we really handle this data? So this is the fourth chapters, and in this seminar I will really be talking about the first three chapters in details. So okay, let's give you some background of my thesis. By background, I mean that I'll talk about the data sets that I have used, the properties of those data sets, and a very brief description of the state-of-the-art ADL detection algorithm I have used in my thesis for validation. So let's start with the data set. As you can see in this picture, I have mainly used two data sets from two different projects. All these are public data sets. So the first in the left side is Castrine project, and the next one is Washington University cases project. So in Castrine, there are three houses. I have collected data, downloaded the data, and then you can see that there are multiple sensor attached to different devices in different rooms. And Washington University cases dataset is a bit more fine, and meaning that there are more users, more activities, and more sensors altogether. So in details, let's see that as you can see here, first three are Castrine datasets, and the next 7 are from Washington University datasets. So as you can understand, first three are all the Castrine datasets are single user datasets, and they kind of have duration of 1 month or half a month, and then the sensors are context sensors mainly. And in the Washington University, whereas there are like various sets of users, there are one user, there are two user, and even multiple users, like 24 and 400 sensors. There are lots of different types of sensors, and a very huge amount of data is getting generated for mostly over a year also. So the last data set is basically an assisted living facility. So there are lots of users and lots of data, and then many events are getting generated. So that is the data set we have. And then next is basically the ADL detection application. So there we have restricted ourselves to just machine learning algorithms, because the deep learning algorithms need a lot of data, which is not really publicly available for such intent processing. So we basically talk about, we have used these three main state-of-the-art benchmark detectors. These are widely used and already very standard data sets for standard algorithms for detecting activities of daily living. So with that in mind, so let's move on. And the first chapter is basically event segmentation in IoT-enabled smart homes. So this was accepted in InfoComm 2016, and then we extended it and submitted it to TMC, which was accepted in 2018. So okay, so let's talk about the problem. We call it TSFS, and it is a data-driven demultiplexing approach for event segmentation in smart homes. So as you can see here, that in the picture in the left, the Castrine home, if you remember, and all the data is coming. You can think of it as a time series. All from various rooms, data is coming a person maybe is interleaving, but all the data is coming in a time series. And then what we will try to do, the objective is to demultiplex the activities of daily living in this event stream, and where each segment will basically tell you what activity is going on. So whether it is eating, flushing, living, or whatever. So properly segmenting is important so that we can detect these activities better. So that is the first problem. Let's talk about some definitions. So what we say is that if on segment, we also call them transactions. If a transaction is basically a segment, which if it is properly segmented, meaning that one segment is one activity, then we call it proper cut. But if an activity is divided into two segments, then or more, then we call it overcut. And the opposite is undercut, meaning that more than one activity is getting mixed in one segment or one transaction. So that is undercut. So the real objective of our theme, this chapter, is to maximize proper cut and minimize undercut and overcut. So let's talk about the intuition of behind this approach. So we have basically three main intuitions that we have worked in. So the first intuition is that a particular human activity spans for a fixed duration. So there's a temporal bound to activities, and then the next is that not all senses that trigger together is a part of single meaningful activity, and the third is that the frequency characters are very different when more than activities are getting more than one activities are getting multiplexed. So okay, let's look at the map. It's a big map, but don't get overwhelmed. It is very simple. It is that first we talk about the segmentation, and then we talk about some detection and stitching. So let's just quickly move on to the segmentation part, where we have these three intuitions. We have utilized it for segmenting the sensor stream. So this is a bigger blowing, if we blow that small box, we have this three cut called temporal cut, sensor cut, and frequency cut. Let's go through them one by one. And first is temporal cut. So temporal cut uses this intuition that there generally between two activities there will be a significant time gap, and within one activity the events will come faster. So if you kind of identify a threshold that is basically lesser than the minimum activity time gap and bigger than the maximum event time gap, then you will probably will be able to segment them well. So if you can see here, between activity 2 and activity 3 and 4, the gap is really big. And even in case of activity 2, between two events, the gap is big. So in this case, it is wrong, and then they're cutting it. But you can roughly identify a threshold that will give you some sort of segments that can roughly resemble activities. So in this case, only activity 1 was properly cut, but activity 2, activity 3, and activity 4 are not getting cut well because of the temporal threshold is not perfect. They will not cut when activities are multiplexing because they'll be close, and if one activity is sparse, then they'll not be able to cut. So this is the very basic first temporal cut that we do. Then next we move on to the sensor cut. So what sensor cut intuition is basically says that same activities will have high similarities. So if you see in this case, activity 2 was cut in two activities by temporal cut. But if we go do some sort of sensor distance that is there in the formula, so I'll not go into the details, but the idea is that you can cluster them, you can find out similarities between two pairs of sensor, one pair of sensor, and then cluster them if they are divided in two activities, or if in the same activity they are not matching, then you can divide them. So in this case, activity transaction 2 and transaction 3, the similarity is very high. A small number is high similarity, so you can basically add them together. So sensor cut is able to get transaction 2 well by combining transaction 2 and transaction 3. But you see that undercut is not really getting resolved. Overcut is resolved probably, but when undercut, meaning two activities are getting, two similar activities that two are getting together in one segment, then it is difficult for sensor cut because it will always say that they have high similarity. So in this case, what do we do? So which is why we come to the next cut, that is frequency cut, which basically says that if there are two activities or more than one activity in one segment, then probably the coming of the sensors will come really fast, and meaning that you can cluster based on how the frequency distance between each pair of sensors are. So we kind of do some sort of training in the ground truth data and find out what is the general frequency between event pairs when they are in a segment, and then try to put that here and come up with whether whether two sensors are coming really fast in time, and then we can divide them. So this is a frequency cut, that based on frequency, event pair frequency, you can basically demultiplex two activities there that may have gotten together, which are very similar in nature. So with that, the segmentation is complete, and so the left part is done. Now let's move on to the activity detector and the activity stitcher part. So activity detector is very simple. After you have gotten the transactions, you run a machine learning algorithm, in our case NBC, HMM, and FIM, and you find out some labels for them from the training and testing. You find out that these are cooking, eating, and drinking water. And what stitching is very simple. It basically looks into the labels of the segments which is detected by the detector and just release stitches. It may look very simple, but we have seen that it greatly reduces overcut and increases proper cut. So that's the idea of stitching. So we are done with the complete framework. So let's talk about evaluation, and the baseline methods we have used are basically temporal methods. We used mean cutter, which is the mean is basically interactivity, the mean of the interactivity times, and then median cutter, which is median of the interactivity times, and percentage cutter is something that uses the ground truth level to find out an optimization, minimizes the percentage of overcut with a fixed set undercut. So I'll not go into the details, but these are the three temporal baseline methods that we have used to compare our results with. So the first result is proper cut, how we really maximize are able to improve proper cut. So as you can see, the last two bars are of TSFS before stitching and after stitching, and both are really high as compared to the mean cutter. So we compare it with the normal mean cutter, and we see that we get to about 200% improvement after stitching. So proper cut really improves after we have segmented the sensor stream. So that is first, and the second is that by improving proper cut, what do we really mean? Whether do we increase the accuracy of the ADL detection algorithm? So here you can see the table is basically tells that for all the methods that are like all the detectors like NBC, CRF, HMM, FIM, TSFS cutters really does quite well. And for FIM, it gives about 93% accuracy of detecting activity. So once you have really segmented the activities well, the activity detection performance also increases. And next we talk about how much we are able to preserve the events in a segment. So even though the activity is in detection accuracy is increasing, are we able to preserve the event characteristics? So as you can see here, the black line is basically for TSFS, and this graph says that the frequency deviation is within 2 standard deviation for 80% of the time. So we are really able to preserve the underlying event pairs in one segment. So this is a very important result. And as I told before, that stitching greatly improves proper cut by reducing overcut a lot. So from 20%, it went to about 80% improvement in case of proper cut by stitching. So even though it's a greedy approach, it does really well. So in conclusion, we can say that we propose a 4-step iterative data segmentation process, which improves the ADL detection accuracy to about 93% of the mean cutter, Oracle cutter. Okay, so let's move on. Let's move on to the next chapter of my thesis, which is DETECTIF, Unified Collection and Detection of IoT faults in smart homes. It was recently accepted in WOW-MOM 2020. So, okay, let's, if you remember from our earlier discussion that smart home generates a lot of data, which is a sensor event stream, and then you go ahead and segment, and after segmenting, you try to detect what activity is happening. But what happens when there is fault in the sensor stream? So if there is fault in the sensor stream, then the segmentation will be wrong, and as a result, ADL detection accuracy will also suffer. So there could be various kind of errors that can contaminate the sensor event and hamper the accuracy of ADL detectors. So what kind of faults are there? Okay, so you can look at sensor faults from two perspectives. One is duration and another is type. And by duration, I mean that there can be three things. Like first is permanent, meaning that a sensor is has failed permanently due to some sort of hardware damage perhaps. And the second is sporadic, meaning that there is a certain random change in the sensor characteristics which is not normal. So it can be like a voltage drift. And the third is transient, which is in the middle of these two, and which can span for quite a while due to some environmental condition. In this example, it is that sunlight is causing some motion sensor to act faultily. So that is of, and when the environmental condition is removed, then the sensor is back to behaving normally. So that is a transient fault. And if you look into from the type perspective, then there are missing faults, meaning that a sensor which was supposed to give some sort of value, it is not giving, due in this example due to some obstruction, perhaps due to some furniture or glass wall or things like that. And then there can be false alarm events, which means that this is not related to the human, but due to some other circumstances. So as you can understand that these two perspectives are really can match with each other, meaning that missing can be of any duration. It can be permanent, it can be sporadic, or it can be transient. And similarly, permanent can be both missing and false alarm events. So these are really same, but two different perspectives. What we do in our work is that we try to build a way to find and isolate both missing and false alarm faults of varying duration in a smart home generated sensor stream in a unified manner. So we look into this entire spectrum and try to detect whether a smart home sensor event stream is faulty. So before going to the approach, let's define our own sensor fault type. So we are really looking into type here in the type perspective. So if first, let's see what we call missing. So missing is basically if a sensor in a segment is said to exhibit a missing fault if it fails to report values that should have been legitimately present. So as you can see in the example that S2 was initially present in the original activity segment, but it is missing. So due to probably some sort of obstruction, so it is missing fault. The second is atypical. So atypical is basically, if you remember the sunlight example, that S2 was present. Now also in the faulty segment it is present, but it is not giving a right value. It is giving some sort of spurious value. So even though it is getting activated, it is giving spurious value. So it is a not typical fault, so we call it an atypical fault. And the third is spurious. So spurious is basically against false alarm, but it is not activated due to human at all. So it is getting activated due to some separate external factor like a pet opening a door, or some voltage drift in a different place, something like that. So it's a complete spurious event that was not part of the original segment at all, like S5 in this example. So so these are the types of faults that we look into, and we will try to evaluate based on these types of faults. So okay, so okay, let's jump into the approach. And the approach is basically, we have two approaches, activity oblivious and activity weighted. I will talk about them in details, but to give you a rough idea, activity oblivious is basically when we don't care what underlying activities are there, and activity weighted is when we try to see what activities are getting predicted, and then try to detect what faults are there. So, and then after you see in the two ends are activity oblivious and activity weighted, we can use one of them, and then we go ahead and detect and correct those faults. So okay, let's jump into the activity oblivious training. So what we basically try to do is we have very simple steps. First is that we try to identify frequently occurring subsets. With that we add some sort of sensor statistical features, like sensor was on, how much sensor was off, whether it was on, how many times it was on, and things like that. And then we try to predict whether a sensor is faulty in a test segment. Now this is the activity oblivious. It doesn't care what activities are there. But if you think about it, if you give this faulty sensor stream to an activity detector, it will still give you an activity prediction. But we don't use just one activity. We use that entire spectrum of with what probabilities, with what activity has been predicted, and then try to match it with our previous finding, that is frequently occurring subsets, and adding features, and then see whether we are able to detect a sensor is faulty or not. So these are the two approaches, and as you can see that in both cases the first two boxes are same. We have to identify frequently occurring subsets and then add it with sensor event personal features. So okay, so what do we mean by frequently occurring subsets? So this is a very simple association rule. As you can see here, there are 6 instances of cooking, and there are different sensors are getting activated in these instances. So from that, if you apply association rule, you can find out with you can come up with some rules like this, that microwave, fridge and oven are generating kitchen door to get activated, and in this case antecedents are the left hand side and the consequent is the right hand side. And for association rule we also have two we also have two things like support and confidence. So support is basically how much this entire things like the microwave, fridge, oven and kitchen door was actually activated together in the entire data set. So this is 3 times by 6, so 0.5, and confidence is support of the entire rule by the support of antecedents. So 3 by 6 by 4 by 6. You can see the color codes and find out the confidence is really 0.75. So you can come up with association rules for the entire data set like this, and then go ahead and add the features, which I mean that, so if you remember, the same rule is there, and then what we do is basically for each sensor that is there in the rule, we kind of add their statistical feature, meaning that when all these 4 were together triggered in one segment, then how much microwave was on, how many times it was off, what was the duration of its on and off. So we come up with statistical features like mean, standard deviation and mode of these features, and like the same microwave, we also do it for fridge, oven and kitchen door. So we add this external features, statistical features with the actual rule and build a master rule set. So the master rule set for activity oblivious is just one master rule set, because there is no activity wise discriminations. But for in case of activity weighted, we have k master rule sets for k activities. So this is the first 2 blocks, and then after we have done this, we will now try to identify some faults. So before doing that, let's find out what regularity is. So we define a term called regularity. It is essentially matching pattern. So we basically say that one sensor in a test segment is regular if it matches with its original behavior in a rule. So regularity 1 is that if the characteristics of sensor is that is a part of a test segment matches with its regular characteristics in the master rule set. By regular characteristics, I mean those external statistical features that we computed for each sensors in rules. So this is what regularity is essentially is. So after this, we will see how we really detect faults. So if you remember, first let's talk about how we detect atypical faults. So if you remember the sunlight example, that a sensor is there but it is acting weird. So now it is where the regularity feature comes. So we are basically for each sensor, we see that whether for each rule, if a consequent is part of the rule and the segment, then we see whether the consequent is acting weirdly, meaning that whether in the rule the behavior was same or not, whether the regularity is 1 or not. If it is 0, then it is a atypical fault. Similarly, let's talk about missing fault. So what we do is that if the consequent of the rule that was there is not part of the test segment at all, so then and we also do some sort of anomaly score where we look into the confidence, so that is later. But the point is that if a rule is highly confident, a rule is there and the consequence is present in the rule but not in the segment, that means that probably there has been a missing sensor. So like in case of obstruction. And the third is spurious, that it means that a sensor is classified to be a spurious when a sensor is part of the test segment, but it was nowhere in the rule, neither in the antecedent set nor in the consequent set of that master rule set, meaning that probably the antecedents were there, but the consequent is not present. So basically a sensor is part of a segment, but it is not, you cannot find it in the rules. So it is a spurious case. Like in this case, pet is opening a door. So a different door altogether. So that is a spurious fault. Okay, so let's talk about the evaluation. We have two baseline strategies, clean and idea. Clean it detects sporadic spurious faults, and idea detects permanent missing faults. So with that, let's see how our approach does as compared to these two baselines. So clean, let's compare it with clean first. That we can see that for spurious fault, as clean just detects spurious faults. And if you see the inset graph here in the left hand side, the clean is doing pretty well at first. The x-axis is basically the fault duration, how long the fault has been. So if it is very small, meaning sporadic, then clean is doing as good as our activity weighted approach. But as time progresses, then the approach that clean uses, it basically fails after some time. So once it is like more than a minute or so, the fault duration, then clean starts to fail. But our activity Oblivious and both activity weighted does quite well. So both precision and recall is higher than clean in case of transient and permanent faults. So that is the first result. The second result is of missing faults. So we compare it with idea. We see that idea really does bad when the duration is very small. If it is of sporadic nature or like a transient nature, like 40 seconds, 1 minute, then it is not doing at all well. If you see the inset graph as well as the big graph, that both the precision and recall is essentially 0 when the fault is sporadic and missing. So again, our approach does quite well as compared to idea, and idea catches up when it goes toward the permanent faults, which it really works on. So then the third fault is atypical. We don't have any baselines to compare with it, but we see that the regularity feature is the reason we really have good about 80% precision and recall as well. So we always see that activity weighted is doing better than activity oblivious, because you are actually adding the reasoning of activities as well, and then matching with your previous belief that whether some sensor is faulty or not. So these are the results. Now talk about the validation, that is the end application. So for all three detectors, NBC, HMM in inset and FIM in original, that you see that the blue line, that is the original data, meaning that if you run FIM and then original data, what is the accuracy that you get. And then if you inject fault, which is the red line, how the activity detection performance deteriorates. So which was our initial motivation, that activity detection performance really does bad when you inject faults, when there is a fault. So we have injected artificially, but that's how it behaves. And then with our methods, we try to detect what faults were there, and then we remove them. After, if you have removed those faults that you have detected, the performance goes up. So it is almost as same as when you had done with the original data. So this basically validates that our method of detecting fault has really worked. So, okay, so in conclusion, we can see that Detective's key novelties include developing rules and adding some sort of external features to increase it. And then those rules are further fine-tuned by considering the probabilistic ADLs, which are represented by the set of correlated senses, and then the accuracy of both the ADL detection algorithm and the fault detection is very high in our approach. So let's move on to the next and the last part of our thesis, in this case, SmartGrade, which is a data gradation scheme in smart homes. It was accepted in Movies 2016 as in a poster, and we have also we are also submitting a journal about this. So okay, so let's move on. As you remember, when I told you the challenges in ADL detection, one is that there's a huge number of data. So the left picture is really a generic graph that tells that there will be more and more sensors and hence more and more data. The right hand side is from our actual data. It basically tells you that the storage has to handle an exponential amount of data every day, and storing and processing such a huge volume of data can be difficult to analyze for the underlying application. And we talk about some opportunities here. So if you see in the right side picture that there is a kind of 3 tiers, and the first tier is performance tier, where it is very expensive, but it is also very fast, which is SSDs. And if you go towards the last tier, and that is hard disk, it is not expensive, but the problem, and it is very like high storing opportunities there, but it is really slow as compared to the performance tier. So now we are trying to say that okay, if the best option is to make available for the application is to make all the data available to them in the main memory itself. But the problem with this is that there's not enough storage, or it is very expensive. So the idea is that you can actually store data in 2 different tiers. You can probably store important data in the performance tier and less important data in the archive tier. So what you really have to do is that you have to identify the context and grade the data and then store it. So that is the opportunity and the intuition that we look into it. And the objective that we can say is that basically, is it feasible to grade a sensor data without dropping the accuracy of an application, and how much space saving you actually can achieve by reducing the data with a good trade-off of accuracy. The third is, what is really the computation cost of doing this process of gradation and storing in different tiers. So if you think about it, the baseline is the complete data and doing the application, and our method is to kind of grade the data, store it differently, and see that how these 3 trade-offs work out. So let's move on to the main map. So again, don't get overwhelmed. There are really 3 parts. First is gradation, second is placement, third is application. So let's go through it one by one. So first is data gradation. So you could think, so there can be very simple gradation, like most frequent sensors are most important, but that is not the case always. Like motion sensors in a home can be very frequently observed, but they are not the most important sensors to identify one activity. But if you can identify correlated sensors, which is that one, as I told before also, that one sensor is activated and because of that another sensor is getting activated, then probably you can do some sort of reduction and see what happens. So what we basically do is we try to find out similarities. So we basically do 2 sorts of similarities. First is cosine similarity, which is very simple. We obtain similarity scores between each pair of sensors. And the second is basically combining 2 graphs. So graph, so spatiotemporal graph and a social graph. So by spatiotemporal graph, I'll tell you in details, but it ideally is a graph of the timestamps and the locations and the sensors, how the relation is. And the social graph is basically how user interactions are, whether they are in the same time, in the same room, and things like that. So we basically run a random walk with restart in these 2 graphs, and then kind of combine these two to find out scores between 2 pair of sensors. So okay, let's go into a little bit of detail. So spatiotemporal graph, as you can see here, the there are three types of nodes: location, sensors, and timestamps, and there are intermediate relations. But what we really have to find out is the relations between the sensors here. So what we do is basically we run an RWR and try to find out some sort of scores. So now we have found out some sort of scores. And what we do is then we see what are the generally the most frequent sensors. We do look into most frequent sensors, and as you can see here, microwave is most frequent, and the relation with it is like the motion sensor and pitch and roll is very highly attached with microwave. So we can say that if microwave is there, they will be there anyway. So we can actually remove those two, and we don't need to put them. Anyway, we understand the context from microwave, and we keep since the relation with fridge is not so high, so we keep it to see whether some different activity is happening, like heating food as compared to cooking. So as you can see here, that we can really remove the motion sensor and kitchen door and just keep microwave and fridge. So that is how we kind of do the data gradation. It's a very simple example, but that's the idea. So we are done with the first two part, that we have found out relevant sensors and correlated them, and then kind of graded them. The next is placing the data into real tier. So okay, how the data placement works, let me quickly tell you that we kind of make a tier of logical volume with two tiers. One is hard disk, the SDB, and the persistent memory, which is a fast tier, which is really as fast as RAM. So this is the storage that we have, two-tier storage. And now we have also have the input data stream, and we have somehow graded it. Now what we want to do is we want to allocate this graded data into the store intelligently. So we do some sort of if allocate. And then what we do is there is a concept called goal. So this is a very integrate file system concept, but very simple to put it simply. It basically tells you where should you store the data. So we tweak some file system files, functions like this map blocks, and we change the goal when we see that the data is coming from higher grade block, and then we store it in the persistent memory contiguously without fragmenting the system. And similarly, we call another function and then store it in the hard disk if they are not important. So that's how we go ahead and store. And the next part that I told you, that the application comes into picture, and when it will try to read the data, if it actually it can read the data from the persistent memory through this function, and from the file system from this function. But we don't really ask the application to read it like this. We do it transparently. So if the application has chosen to get only the important data, it just invokes the read function, and it basically gets the view of just the important files, and it thinks that this is the entire data that I should analyze if it only asks for important data. So it can also get the entire data, as I told, that there's just another option that you have to choose, and then you can get the entire data. So that's how it works. So let's see the results. So quickly, if you can see that this is a reduction as well as accuracy improvement graph that we have, like for cosine similarity and for spatiotemporal graph, we have very, very high reduction. We have almost 60% reduction without marginally marginal accuracy drop. So for some cases, cosine similarity did not work well, but spatiotemporal always actually have good accuracy improvement. The reason behind is that the activity detector is actually able to detect well because there are no redundancies now. So that is the first result. The second is a bit detailed, meaning that how for each activity the system is performing. So if you can see here, again, we are comparing it with just taking the top, saying that, okay, you can just keep the top frequent sensors and downgrade everything else. And as compared to the SmartGrade graph, right? So you see that for the spatiotemporal graph, we always have accuracy improvement, but in some cases, like in leave home, the fourth bar, we see that top frequent is doing better, because in this case, again, the top frequent sensor is motion sensor, which is playing a heavy role in this activity. So sometimes it is good, but most of the time our method works better. and hence has a average high accuracy improvement. The third is trying to see whether the runtime improvement, the throughput of the entire system is increased. Now, if you understand, the application is now getting really small data as compared to the entire data. So which is why the runtime improvement of the entire system improved. So if you see here in the left graph, with the actual data, we have about close to 10% runtime improvement. And what we did is we scaled the data and we saw whether that works. So we scaled with Smooth, and we see that even with 10x and 20x scaling, we have even high runtime accuracy, because at that time you identify even more redundant data and the application is getting very small data. So the runtime improvement is very, very high. Now, as you can see here in the right graph, we also handle overflow, meaning that here we have only considered a PM of 512 MB, and we basically see that when you have overflowed a higher tier, the high grade data is also now getting stored in hard disk, but the application is still getting just the high grade data. So even though runtime accuracy is decreasing after a while when the data size is increasing, but it is still good. The runtime improvement is still good because the application is still getting less data. So we also provision for overflow situations. So in conclusion, you can say that we have an application independent gradation algorithm, a two-tier storage, and finally a faster and transparent access to the application. So let's summarize it. We have these three processes: TSFS, DETECTIF, and SmartGrade, which handles and ultimately improves the accuracy of ADL detection algorithms. These are thesis publications, one journal, and there are 3 conferences and 1 poster paper. So thank you everyone for listening, and that's